All right, new section, section 3.4. We're going to learn integration by substitution, which is challenging, fun, maybe, very important, definitely. It's a big section in a calculus class. What this is a method to help us figure out antiderivatives when our functions are a little bit more complicated. And maybe integration by substitution is the technical name, but most people refer to it as U-substitutions or just for short U-subs. So what we'll be doing in this section is learning how to use U-subs to take antiderivatives. And you might be wondering why we need this new method, and basically the short answer is because there's a lot of functions that we don't know how to take the antiderivatives of. Right? We learned in 3.3 rules for the more basic antiderivatives. So for example, if I asked you to take the antiderivative of 3x squared plus 1 over x dx, because we have two different terms in here, we can break this up into two different antiderivatives. And because this 3 is a coefficient, we can pull that out in front. We can rewrite this problem as 3 times the antiderivative of x squared dx plus the antiderivative of 1 over x dx. Which is cool because we can just look at these and figure out the antiderivatives for x squared and 1 over x. For x squared, we're kind of undoing our power rule. So you add 1 to the exponent and you get x cubed. But then you remember that it's not enough to just add 1 to the exponent. I'll have to think about if I took the derivative of this, I'd get 3x squared, not just x squared. But I don't want that extra 3, so I need a 1/3 down in front here. So that this 3 cancels out with this 1/3 and leaves me with this 3 for my 3x squared. And then I move over to this next integral, where I have to take the antiderivative of 1 over x, and the antiderivative of 1 over x is the natural log of x, technically the natural log of the absolute value of x, although sometimes I leave out the absolute value symbols and just assume that x is a positive number. But technically I should put in the absolute value symbols in there, and then if I'm talking about things that I should technically do that sometimes I forget, I should tack on a plus c. We learned in the previous section how to take some antiderivatives, and I think you're at the point where if I give you a function like this, you can find the antiderivative of that function. Guess I could even clean this up a little bit and call it x cubed plus the natural log of the absolute value of x plus c. That was meant to be a quick little review of what we learned in the previous section, because in this section what we're going to do is kind of build on that. We're going to be like, all right, cool. I mean, I can take the antiderivative of this function because really the reason I can take the antiderivative of this is because the derivative of this isn't that complicated. Right? If I were taking the derivative of this, the derivative of x cubed is just 3x squared, which shows up right here. And the derivative of the natural log of x is just 1 over x, which shows up right here. The derivative of a constant is 0. Like, it's not that complicated to take the derivative of this answer to get back to this question. And that's why I'm able to figure out this antiderivative to begin with. But then if you think back to chapter 2, we took derivatives of really complicated functions. So imagine the case where we have to use the product rule, or the quotient rule, or the product rule inside the quotient rule, or the chain rule combined with the product rule or something. If we took some really, really messy derivative, we'd get this huge disaster of an answer. And if I started you out with that huge disaster of an answer and asked you for the antiderivative of that, would you be able to undo that derivative? And the answer is, well, no, not until you learn some tools and tricks and tips on how to do so. So what we're going to do is we're going to start to learn how to undo these different derivative rules. And that's going to be kind of a big undertaking, so we're going to start with just one of them. In this section, U-substitutions, we're going to learn to undo the chain rule. So how do you undo the chain rule? Okay, first I need to remind you a little bit about the chain rule. Suppose you're trying to figure out the derivative of, maybe I need an extra set of parentheses here, x squared plus 3x plus 1 to the 5th power. The way I kind of taught you to do this is I said, think about this like you're taking the derivative of something to the 5th power. And that something just so happens to be a function in its own right, x squared plus 3x plus 1. The way I told you to view this problem is to kind of think about it in layers. You got the blue layer and the green layer. The green layer is kind of the inside layer. The blue layer is the outside layer. So when you're taking the derivative and you have layers like this, functions composed together, you first deal with the outside layer. So I take the derivative of the stuff raised up to the 5th power, bring the 5 down in front, and subtract 1 from the exponent to get 5 times something to the 4th power. What is that something? Well, you might think you should take the derivative of x squared plus 3x plus 1 and put it right here, but you don't. The way you use the chain rule is you leave the green stuff completely alone inside the blue stuff. So I got x squared plus 3x plus 1 here. But then you're not done. Since we haven't taken the derivative of the green stuff, we have to multiply that at the end. We have to multiply by the derivative of x squared plus 3x plus 1, which ends up being 2x plus 3 in this case. The derivative of x squared plus 3x plus 1 to the 5th power is equal to 5 times x squared plus 3x plus 1 to the fourth power times 2x plus 3. And you're like, yeah, we got lots of practice with the chain rule. I can do that. I'm like, all right, cool. Well, then figure out the antiderivative of 5 times x squared plus 3x plus 1 to the fourth power times 2x plus 3. You want the antiderivative of this thing. Well, a minute ago, I figured out the derivative of this thing was this thing. Therefore, the antiderivative of this thing is just this. My answer, that's simple. It's just x squared plus 3x plus 1 raised up to the fifth power. And if I'm being really technical, maybe I tack on a plus c. I'm like, yeah, that's great. That's awesome. And you're like, so what did I just do there? I'm like, you figured out a really, really hard antiderivative. And you're like, well, not really, right? The only reason, presumably, you're able to come up with this answer is because I just asked you this question. If we hadn't just done this question right here, if we didn't have this written right above, you probably wouldn't be able to figure out that the antiderivative of this mess was this thing. Or even if you could somehow figure out that the antiderivative of this was this, which I think would be asking a lot, I could probably mess with the numbers a little bit and make it kind of not work out quite so perfectly that you wouldn't be able to do that, right? I could rewrite this integral as, maybe I take the 5 and distribute it into the 2x plus 3 and get 10x plus 15, and then multiply that by x squared plus 3x plus 1 to the fourth power. If I just rearrange these terms right here to write the question slightly different, I bet I've confused things enough that if you started right here, you'd be like, I have no idea how to find the antiderivative of this. But that's okay, because you haven't learned the chain rule yet. I'm just trying to motivate the need for the chain rule. And the reason we need the chain rule is because taking antiderivatives of something that looks like this is really, really hard, especially if you hadn't just taken the corresponding derivative a second earlier. You're like, all right, I get the point. Like, we definitely need this rule. You got me thoroughly confused. Can you please just tell me how, if I see a problem like this on a quiz or something, I can figure out this antiderivative? I'm like, yeah, absolutely. The key for this problem, or any of these that we've done so far, is recognizing that the thing we're trying to take the antiderivative of, it's called the integrand. The integrand contains an expression, in this case x squared plus 3x plus 1, and it also contains the derivative of that expression, 2x plus 3. The key to using a U-substitution will be recognizing that inside this big mess, I have something, I'm going to end up calling it u, and I also have the derivative of that something, u prime. Wait, why is that so important? Why does it matter that I have a function and the derivative of that function? Well, because U-substitution undoes the chain rule. And when you're doing the chain rule, remember, you kind of deal with the outside layer and you leave the inside layer alone. That inside layer is going to be this expression that I'm talking about. How do I know that? Because after I take the derivative of the outside layer, I then have to take the derivative of the inside layer. So I end up with the expression and the derivative of that expression because of the chain rule. So since the whole purpose of U-substitutions is to undo the chain rule, we'll be looking for instances where we have an expression and we have the derivative of that expression. Okay, you still haven't shown me how it works. I know, I'm getting there, trust me. What I want to do now is take the derivative of something very similar. Instead of x squared plus 3x plus 1 to the fifth power, I want to take the derivative of u to the fifth power. Note that my variable of integration here is still x. So this u is going to represent a function. What I want you to think is related rates, a topic that we tacked on at the end of chapter 2 that was probably pretty confusing and you thought you'd never see it again. Using the methods of related rates, could you take the derivative, assuming x is your variable and u is a function, of u to the fifth power? I think you can. I mean, essentially the way I taught you to do this is treat u like it's a function, so you got the chain rule going on here. The outer layer is the stuff being raised up to the fifth power, so you take the 5 down in front and subtract 1 from the exponent to get a 4 right here, and then you leave the stuff on the inside, a u in this case, completely alone. But then you're not done, you have to multiply that by the u prime. Maybe the method that we do right here feels very similar to the method that we did up here. We took the 5 down in front, changed the exponent to a 4, left all the stuff on the inside completely alone, but then multiplied by the derivative of that stuff on the inside. The point is, using related rates, the derivative of u to the fifth power is 5u to the fourth times u prime. What that means is that the antiderivative of 5u to the fourth u prime must be equal to u to the fifth. right? Because this is just saying undo this process. If the derivative of this is this, the antiderivative of this is equal to this. But take a closer look at what this is saying right here. I'm taking the antiderivative of 5u to the fourth times u prime. And what I get from my answer is u to the fifth. U to the fifth is the antiderivative of 5u to the fourth if my variable were just u. But because u isn't just a variable, it's a function, I tack on this u prime. If I'm trying to take the integral of something that has some expression, the letter u, and it also has the derivative of that expression, u prime, when I take the antiderivative, the u prime essentially goes away. Because look, if we're taking the antiderivative of 5u to the fourth, and we're not thinking in terms of related rates, and we're just treating the u like it were the variable, the antiderivative of 5 times a variable to the fourth power is just the variable to the fifth power. So because the u prime kind of, loosely speaking, magically appears at the end of this derivative, the u prime, loosely speaking, magically disappears when I take the antiderivative. If we can look at an integrand and see an expression and the derivative of that expression, we'll be able to, loosely speaking, ignore the derivative of that expression when we take the antiderivative. And that's exactly what happened way back up here. I had 5 times some expression to the fourth power times the derivative of that expression. And because I had the derivative of that expression in here, essentially what I could do when I took the antiderivative is completely ignore all this stuff and just undo the power rule part. This exponent of 4, I added 1 to turn it into a 5, and then I divided by 1/5, which canceled with this 5, and I completely left all this stuff on the inside alone. I can tell this is confusing. Maybe I need to stop trying to motivate why this works and show you step by step how do you figure out the antiderivative if you start out with something that looks like this. So let me do that. I want to teach you an algorithm so that you can do a U substitution step by step. Unfortunately, before I teach you this algorithm, I just got to be a little careful with some notation. So far we've been using this d over dx kind of as a verb, right? When I write d over dx x squared, this means take the derivative of, and then whatever's in the parentheses, x squared. So if you take the derivative of x squared, you get 2x, loosely speaking. We've been thinking about this d over dx as kind of a verb. It's telling you what to do. But we can also use it as a noun. We haven't done this in this class, but it's pretty common. If somebody gives you a function, instead of saying f of x equals x squared, in which case you can say f prime of x equals 2x, another way you can convey that exact same information is you could say y equals x squared. To talk about the derivative here, some people might write y prime equals 2x, and that's totally fine, you can, but what some people do is they say the derivative of y is equal to 2x. And maybe that kind of makes sense, right? If the y is x squared, the derivative of that y is 2x. And it turns out people don't typically leave it this way. People kind of treat this symbol almost like it's a fraction. This d over dx times y, it's not really times y, it's the derivative of y. But if it were times y, then you'd be able to write it as dy over dx. And since that would make a lot of sense, a lot of people use this as a symbol for the derivative of y. So instead of saying f of x equals x squared and f prime of x equals 2x, I could say y equals x squared and dy over dx equals 2x. In this context, the d over dx kind of acts like a verb. It's saying take the derivative of x squared. Down here, it kind of acts like a noun. The derivative of this function is 2x. This notation will be really useful for the algorithm that I'm finally going to show you and then end this video. So I wanted to make sure that I introduced it. Here in all its glory is the U substitution algorithm. There's really 3 challenges with the U substitution algorithm. The first one is recognizing that you have an integral that needs to use the U substitution algorithm to begin with. That'll be fairly easy in this section because in this section all the integrals we're going to deal with will require this algorithm. But generally speaking, it's a big challenge just recognizing that you want to use the U substitution algorithm. Generally, the way you know you're going to use the U substitution algorithm is when you have an expression, like x squared plus 3x plus 1, and also the derivative of that expression, 2x plus 3, all inside the integrand. The first step in your U substitution algorithm is deciding what you want U to be equal to. In this case, we're going to let U be equal to x squared plus 3x plus 1. I'd argue that the hardest part of U substitution is this first step. It's determining what U should be equal to. It's hard to know that you should be using U substitution to begin with, and even if you know you should be using U substitution, it's hard to know what U should be equal to. We'll get a lot of practice figuring out what U should be equal to. So for now, maybe just trust me that in this problem we want U to be equal to x squared plus 3x plus 1. The first step is determining what U should be equal to. The second step is taking the derivative of U. However, we're not going to write it as like U prime. We're going to use this new notation. So if U equals x squared plus 3x plus 1, then du divided by dx, the derivative of U, where x is the variable, would be equal to 2x plus 3. First step, determine U. Second step, take the derivative of U and write it as du over dx equals 2x plus 3. The third step is a really strange one. Up until this point in the class, this has not been a fraction, right? This is just a symbol that acts as a noun that tells you the derivative of U. However, the reason this symbol is used in the first place is because in some instances, you can kind of treat it like a fraction. And you're like, well, what do you mean treat it like a fraction? If this were a fraction, you could multiply both sides of the equation by dx. And if you did that, you would get du is equal to 2x plus 3 times dx. You probably don't feel comfortable doing that because this is not a fraction. However, in this very specific instant, it kind of works like a fraction. So your third step is to treat this symbol as though it were a fraction and multiply both sides of the equation by dx. It's kind of a confusing step, but at least it's an easy step, right? Once you've gotten 2, getting step 3 is really easy. That brings us to step 4. In step 4, what you want to do is substitute step 1 and step 3 into the original question. And maybe parenthetically I should add, you have to do these substitutions so that what you end up with doesn't have the letter x anywhere. All of the x's need to now be u's. However, the good news is if you've done steps 1, 2, and 3 correctly, you'll be able to do step 4 in such a way that all the x's are gone. How? Let me show you. Maybe some color coordination will help. This was the original question that I was asked, right? The antiderivative of 5 times x squared plus 3x plus 1 to the 4th times 2x plus 3 dx. But in step 1, I figured out that u was equal to x squared plus 3x plus 1. So what I can do is I can replace this x squared plus 3x plus 1 pictured in green with the letter u. That leaves me with 5u to the 4th times 2x plus 3 dx. But remember, I need to change all my x's into u's, and I also need to substitute equation 1 and equation 3. Equation 3 tells me that du is equal to 2x plus 3 times dx. Note that what I have left written over here in blue is exactly 2x plus 3 times dx. So since 2x plus 3 times dx is du, I can replace exactly what's written here in blue with du. What we now have is a question that we're well equipped to handle. This is an antiderivative you can figure out. And you're like, I'm not sure if I can. I feel uncomfortable with the u's and stuff. Don't worry about the u's. My variable is u now. Remember, the symbol that I put out here, this du, specifies what letter I treat as a variable. So because I don't have a dx over here anymore, I now have a du over here. I treat u's just like we've been treating x's. They're just my variable. To take the antiderivative here, I don't have to do anything tricky at all. All I have to do are my basic antiderivative rules. I could pull the 5 out in front if I felt like it. Then I'd have to take the antiderivative of u to the 4th du. And I get 5 times, let's see, for u to the 4th, I add 1 to the exponent, but then I got to divide by that 5, and then I tack on a c. I can simplify this if I want. 5 times 1/5 is just 1, so I get u to the 5th power plus c. The antiderivative of 5u to the 4th du is equal to u to the 5th plus c. And you're like, so that's my final answer? Almost. Remember, the original question didn't have any u's in there. You, the student, y-o-u, substituted u into this equation. You don't want to leave u's in your final answer because u is something that was created within this process. So the final step, step 5 in this u substitution algorithm, is just to substitute back. Instead of writing u to the 5th plus c, since u is x squared plus 3x plus 1, my final answer would be x squared plus 3x plus 1 to the 5th power plus c. The nice thing about everything in chapter 3 is, if you're not sure about this answer, just take the derivative. Taking the derivative, I'd use the chain rule. Using the chain rule, I'd get this is my answer. Therefore, if the derivative of this is this, the antiderivative of this must be equal to this. If this feels like kind of a convoluted method and you're not quite sure you understand, that's totally fine. The purpose of this video was to try to justify a little bit why this works and introduce the algorithm for the first time. In order to really understand this algorithm, what we need are repetitions. So what I'm going to do in the next 2 videos is just do example after example after example, showing you this U-substitution algorithm. Because really, this is something that the only way to learn it is through repetition. It takes a long time. So don't worry if you're a little bit confused right now. Even if you don't think that you could recreate all these steps, if you can kind of see what I did in each of these 5 steps, you're exactly where you want to be. And hopefully I can clear some things up in the next video.